Okay, well, welcome back, everybody. So today it's my great pleasure to introduce Andrew Burbanks. Andrew completed his PhD in 1997 at the University of Loughborough. He then worked at Hewlett-Packard Research Laboratories in Bristol before taking a postdoc in the Department of Pure Mathematics and Mathematical Statistics at the University of Cambridge, and then later in the School of Mathematics at the University of Bristol, where he gained a permanent post as a scientific programmer. He joined the Department of Mathematics at the University of Portsmouth in 2005, where he's now Associate Head for Research and Innovation and a Principal Lecturer. His main research interests are renormalization for dynamical systems with an emphasis on computer-assisted proofs. So today he's going to talk with us about computer-assisted proof for renormalization fixed points and eigenfunctions for period doubling universality and maps of the interval. So Andrew, thank you for joining us today, and the floor is yours.
Okay, thank you very much. Hopefully you can see my slides, my title slide. Yeah, great. Thanks very much. Well, thank you very much to the organizers for creating this seminar series. I was saying it's been a great pleasure over the last few months to see some of these seminars, and thank you for the invitation. So the work I'm going to present is a collaboration with Andrew Osbaldestin and Judy Thirlby. Judy finished her PhD, passed her viva last week with minor corrections, so that's a very good time. And I'd like to thank Andreas Sturman and Ben Mestel for helpful discussions. Andreas was one of Oscar Lamford's PhD students, and the work that I'm going to present goes all the way back to the work of Lamford and others. I'd also like to dedicate this to Michel Feigenbaum, who died recently. So the objects of study here are one parameter families of unimodal maps of the interval. And the prototypical example is the family shown here. We could do away with the modulus there by fixing even integer degree d at the critical point. So these have a local maximum at the origin of degree d. And the case d equals 2, I've drawn the bifurcation diagram below. So we have the parameter going across, and vertically we have the asymptotic behavior for all but a set of measures 0 of initial conditions. So we have the final fate, if you like, at each experimental parameter value mu. And this beautiful bifurcation diagram has been very well studied. The bit that I'm interested in is the bit at the beginning, the period doubling cascade. So certain features of this period doubling cascade are universal, both qualitatively in terms of the type of behavior that happens, but also quantitatively. In particular, so I've illustrated this for the degree d equals 2 case, the ratio of successive spacings between period doubling parameter values converges to some universal constant, often called delta. For the case d equals 2, it's 4.669 approximately. And there's a corresponding universal scaling constant in the state space direction, in the x direction, alpha. For the case d equals 2, roughly minus 2.5. There's a nice picture of Feigenbaum there, in his prime, as it were, working on such results. So the key to sort of understanding why these constants are universal, at least the explanation that Feigenbaum came up with, rests on looking at the dynamics of a renormalization operator R. So this operator acts on functions G by composing them with themselves and then rescaling in both directions. And we choose this scale factor, I've called it A here, it's sometimes called alpha, and you take the reciprocal. We choose that to preserve some sort of normalization that we want on our map. So I've chosen a normalization here that sets the function value at the critical point to 1. So Feigenbaum made a number of conjectures about this renormalization operator, but the chief ones are that it has a fixed point that's essentially of saddle type. So when viewed in the right way, it has the spectrum of the linearization of the operator at the fixed point has basically a single essential expanding eigenvalue that happens to be this universal constant delta. And that helps to explain why delta is universal. So I'll just draw a quick sketch in the space of functions. So here the renormalization fixed point is indicated by G star. and think of it as essentially a saddle point with a one-dimensional unstable manifold and codimension one stable manifold. The truth is a little bit more complicated, but this is a sketch. And the idea is that a typical one-parameter family, such as our prototype family from before, forms some other curve in this space. And if the family has an infinite cascade of period doublings, then that curve passes through the surfaces that I've indicated, these sigma k's. These are the surfaces of functions with a superstable 2 to the k orbit. So a family that undergoes an infinite period doubling cascade forms a curve in the function space that passes through infinitely many such surfaces. And the idea then is that the unstable eigenvalue of the linearization of the operator at the fixed point G star, which is delta, determines the asymptotic spacing of these surfaces, and so also determines what happens for other one-parameter families nearby. And if we were only interested in numerically approximating things, then this sketch gives us a nice way to find an approximation to this fixed point G star. We could use a variant of Newton's method to numerically follow successive period doubling bifurcations up this tree by solving for parameter values that put the critical point on a 2 to the n orbit. So we could search for successive superstable period 2 to the n orbits and move down this diagram close to this stable manifold at the bottom. Then we could apply our renormalization operator, R, and that will sort of hop us across, at least for a while, in towards the fixed point. We can't apply this too many times, of course, because we have this unstable direction that will begin to push us away. And then once we're close enough, we could switch to a variant of Newton's method for the fixed point problem to iterate in towards the fixed point G star. So this is how we can get an approximate fixed point function. So the conjectures of Feigenbaum, historically analytical proofs for these conjectures have been extremely hard to come by and have required some very deep insights into the field and ideas from other areas outside of dynamical systems. But recently, many results have been proved, in fact, for a broad variety of critical exponents D. But a number of these questions were settled first by rigorous computer-assisted proofs. So that's the approach that I want to take today. And these go back to at least to Lamford in the 1980s, Ekman, Koch, and Witwer, and so on. So we've got this renormalization operator R, and we'd like to find a fixed point function, which I've called G star. In other words, we have a functional equation that we would like to solve for this unknown function G star. If I restrict to even integer degree critical points, then certainly we can make this ansatz that our solution can be written as some other function, capital G, of x to the power d. And I'll use the notation capital X for x to the power d. So we can look at then the corresponding operator, which I'm going to call T, on these, if you like, symmetry reduced representations of our function. So it's really a fixed point now of this operator, capital T, that I would like to find. It's easy using the method that I stated earlier and sketched in the function space to find approximate fixed point functions. And here's a sketch of, or rather a picture of a good high degree polynomial approximation to this function G star. And the thing to take in from this diagram, obviously one can tell by eye that something interesting is going on, but the special thing about this function is it's compositionally self-similar. So it has the property that composing it with itself is exactly the same as rescaling it by this scale factor A. This is an approximate solution for the case D equals 4, and that's what I'm mostly going to talk about in this talk today. So finding an approximate fixed point is fine, but what we'd like to do is to prove that there's a true fixed point somewhere nearby in the space of functions, or a suitable space of functions. So the first thing to do is to decide which space of functions we would like to work in. So what sort of objects G star are we willing to entertain as solutions? And the space that I'm going to work in is a space of functions analytic on some disk. So one can immediately tell, because of the composition in the operator, that the only polynomial solutions to the fixed point equation are trivial ones, because composing the function with itself squares the degree. So it's natural then to think about power series. And when we think about power series, we have to think on what domain do they converge. So I'm going to pick some disk omega and look at the set of functions analytic on this disk, satisfying a couple of technical assumptions on the closure. So the important thing to realize, functions in my space have power series expansions which are convergent on this disk. And with the usual sort of pointwise operations, addition, scalar multiplication, product and composition of functions, plus choosing a suitable norm, and L1 turns out to be a good one to pick, we get an infinite dimensional Banach algebra. And I'll take as a shadow basis just the obvious basis elements, the pure powers, if you like, expanded with respect to our disk. So the question is, how can we do rigorous computations in a space like this? And there are two obvious hurdles. One is that the function space is infinite dimensional, so we're going to have to truncate somehow and then bound the parts that we neglected. The second thing is that our computer arithmetic isn't exact either. So the idea is we're going to work with power series truncated after some fixed integer degree n, and then I'm going to let p and h denote the projections onto the corresponding polynomial part and high order part of the space. So any function in our space I'll write as the sum of a polynomial plus high order part. And then the idea, which really underpins everything we do in computer-assisted proofs in one way or another, is to simply give up the idea of dealing with a single object exactly, and instead settle for dealing with a set of objects whose bounds we can represent exactly. So to this end, following the work of Ekman, Koch, and Wittmer in the 1980s, I'm going to define a function ball to be a set of functions in our space that can be written as the sum of a polynomial plus high order plus general part, where the polynomial part has coefficients bounded by intervals that we control, so with endpoints that we control. The high order part is a high order function whose norm we control. And finally, this extra part, the general part, is just bounded in norm. And it turns out it's very useful to have this general part around, well, to begin with, so that we can just talk about a ball of functions in the usual sense, centered on some particular polynomial, but also during the computations, it's useful to be able to absorb some of our error bound into this general part where it would be expensive or inefficient to do so in the polynomial or high order parts. So it's very useful to have that thing around. And the set of functions that we get is convex and closed. The convexity turns out to be very important for what we want to do later. So then the idea is that to do the calculations in the computer, we'll just use computer representable numbers for the endpoints of our intervals and for our two upper bounds. And then for any binary operation that we want to do on these function balls, we'd better design a version that acts on our bounds such that this inclusion is guaranteed. So the ball specified by the result is guaranteed to contain the exact answer. And there's an obvious sort of analogy with interval arithmetic. If we have two reals, x and y, perhaps we can't represent them exactly, but we'd quite like to add them together, then we can bound them within intervals that we can represent exactly. And provided that we have access to a method for delivering as a representable lower bound on the sum of the lower bounds and a representable upper bound on the sum of upper bounds, we can come up with a new interval guaranteed to contain x plus y. So this should all be very familiar. In a similar way, Ekman, Koch, and Wittmer in the 1980s published a very detailed framework, in fact, for functions of two variables, in which they showed that it's possible to bound all of the operations that we're going to need, including addition, scalar multiplication, product, composition, provided that G is a nice enough function with bounded suitably in the norm. One can bound the norm. One thing that we can't bound directly is the derivative of a function ball, and one might want to have a quick think about why that's the case. The corresponding differential operator isn't itself a bounded operator, so we can't do that, but we can bound derivative followed by composition if the function g satisfies suitable conditions on its norm. So it turns out that we're able to bound all of the operations that we need. So the question is, now we've got a way of doing computations in our function space, how can we prove the existence of a true fixed point G star close by to an approximate one? And the idea here is that, well, we might think of iterating our operator T itself. However, it has this expanding direction corresponding to this eigenvalue delta. So it's no good if iterating the operator itself. However, we might hope that close enough to a true fixed point, a Newton operator would be a contraction on a small ball around an approximate fixed point. So we'll pick a Newton-like operator, which I've defined here. dtg is of course, the Frechet derivative of our operator T at the function G. So the idea is to show that an operator like this is a contraction on some suitably chosen ball of radius rho around an approximate fixed point function G0. Before we start this, of course, we'd better first prove that our operator is well defined on this ball, that it is differentiable and that the derivative is compact. So we need to do these various other technical assumptions first. But given that, there are then three ingredients which are probably nicely summarized by this sketch. Firstly, we bound by how far our approximate fixed point moves under our Newton operator by some distance epsilon. Then we gain a uniform bound on the contractivity of our Newton method over the ball, kappa, which means that the image of the ball is contained in another ball of radius kappa rho. And finally, we verify this third inequality, which just proves that the smaller ball really is contained inside the larger one. So we might need that this ball is mapped into itself. Then the contraction mapping theorem will give us the existence of a locally unique fixed point in this ball B1. So the technical bit of this bound really is step number 2. So I'll describe that in a little bit of detail, how we get this uniform bound on contractivity. And the idea is to just borrow ideas from finite dimensional calculus and use the mean value theorem. Because our function balls are convex, the line segment joining any two functions within a ball is contained within the ball, and we can essentially reduce things to a one-dimensional argument along line segments. So the idea is we're going to bound the derivative of our Newton method and use this to get a bound. Now, of course, bounding the norm of the derivative, if we think, for example, of the operator norm, this is an uncountably infinite calculation to do because we need to bound things over the unit sphere in this case. But we can reduce this to a countably infinite calculation by realizing that if we're dealing with L1 at least, then a bound on the norm of the action of our derivative on all basis elements is enough to give you a bound on the operator norm. So we've reduced things from an uncountably infinite calculation to a countably infinite one, which we can then turn into a finite computation as follows. Basically, we will bound the action of the derivative on all of the polynomial basis elements. So there are n+1 of those. And then we can get a bound on the infinitely many norms that remain by realizing that a single function ball of high order radius 1 contains all high order basis elements. Of course, unfortunately, it also contains a lot of extra stuff too. So the bound one typically gets here is pretty loose. This is the convex hull of all of the high order basis elements. So this is a non-trivial function ball to start with. So this is really the limiting factor in the computation. But we reduce things essentially to n+2 calculations that we need to do. Okay, so I'll just return briefly to the little technical point that I skimmed over, which is how we prove that our operator is well-defined, differentiable, and the derivative is compact. And the key for sort of composition and rescaling operators like this turns out to be to look at the functional form of the operator and look where our function, in this case G, is applied, and then ensure that the argument functions preceding that map the closure of a domain strictly inside itself. So it turns out that if one could, which leads to the two conditions I've listed here. So if one can prove this, then it turns out that one can show that the operator is differentiable. Well, certainly it's well defined, that much is obvious, I think, from that. but one can also prove that it's differentiable and the derivative is compact. So how we do this, so I've demonstrated this for the case d equals 4, so I can find a suitable disk domain, and I cover the boundary circle of the disk with a number of small rectangles, and then use rectangle arithmetic, which is the obvious complex extension of interval arithmetic, where one has intervals for real and imaginary parts. A crucial factor in this is the, if you like, the amount of wiggle room one has here, which is often expressed in terms of a number called the analyticity improving factor. And for this particular choice of domain, there's plenty of room here, it turns out. Okay, so one can do this for the case d equals 4. A second technicality that I glossed over is the following, that we want to look at the contractivity of our one-step Newton operator. Here's the one-step Newton operator itself. That means taking its derivative, but the expression for it already involves the first Frechet derivative of t. So we're going to end up with an expression involving second Frechet derivatives of t, which would be quite unpleasant to deal with. And we also have this inverse to cope with. Now, in principle, one could probably do this, but it's much simpler to realize that we could choose some other invertible linear operator, gamma here, and instead consider this what you might call a quasi-Newton method, a simplified Newton method, which shares the same fixed points as t does in any case. What's more, obviously, so we've got quite a bit of freedom in what to choose for that operator, but it would be a really good idea to choose a good approximation to the original expression at the fixed point. But what's more, we can save ourselves some heartache by making this a fixed linear operator, so that derivative terms don't appear when we take the Frechet derivative of the Newton method. So with all of that in mind, the Frechet derivative of this quasi-Newton method just looks as follows and involves just the first Frechet derivative of our operator t now. So that's a considerable simplification. How does this Frechet derivative look? Well, here's a sort of formal expression for it. I've highlighted in blue the places where the variation of g, the perturbation delta g, appears on the right-hand side. So dt at g acts on some perturbation function delta g and maps it into this expression here. And I've also highlighted places where the derivative function g prime appears. And you'll notice that what's convenient for us, derivatives only appear in compositions with other functions. And it turns out that from our domain extension conditions that we satisfied earlier, that they have suitable norms, which mean that we can bound this derivative followed by composition. Okay, so the good news after all that is that we can take this computation forward. So in the case d equals 4, a truncation degree of 40 is sufficient. I wasn't able to get it working with anything shorter than 40, which means degree 160 for our original fixed point function g. And working to 40 significant figures using multi-precision, one gets a function ball of radius about 10 to the minus 20 containing this fixed point function. An immediate consequence by evaluating the functions in our ball, we gain bounds on the universal constants a and alpha, which is 1 over a. So one gains intervals containing these universal constants. And in the pictures, I've just demonstrated how one can come up with a rigorous covering of the graph of the function itself. So on the left-hand side is our sort of symmetry reduced function, capital G. Incidentally, one might want to have a think of what's the meaning of the values of capital G for negative x, because for degree 4, one only evaluates capital G at capital X greater than or equals 0. So in fact, what we gain is the values for the universal function g star on diagonal rays in the complex plane. They're encoded as the values of this sort of symmetry reduced function g for negative x. And on the right hand side is the function we're really interested in. So g of x, which is capital G x to the d Okay, so we can bound this function and get a successful computer-assisted proof. So this really goes back to what Lamford did in the 1980s, but for the degree d = 4 case. But what I was interested in next was trying to sort of take these things a bit further and ask the question of whether we can get bounds on the spectrum of the derivative of our operator and whether we can bound associated eigenfunctions using similar methods. So first, let's have a look at the spectrum of our reduced operator capital T, or rather of its derivative at the fixed point. The fact that we are able to establish that this derivative is compact means that it's as close to acting like a finite dimensional linear operator as it's got any right to be, by which I mean that aside from the origin, its spectrum only consists of isolated eigenvalues of finite multiplicity, which is the nicest thing we could possibly hope for, really, in the infinite dimensional case. So it turns out that the spectrum of the derivative of t in a fixed point actually has two expanding eigenvalues, alpha to the d and the one that we really want, delta. And so there's an obvious question, what's alpha to the d doing there? Well, if you remember when we defined our operator, we put in the rescaling by a in order to preserve some sort of normalization we were interested in, but the operator doesn't enforce that normalization. And this is what typically happens. One gets additional eigenvalues that correspond to coordinate changes, to changes of scale and so on. And so modulo setting our own scale and therefore projecting those things out, we have something that's essentially one-dimensional and stable manifold. Okay, so the first question is, how can we bound this spectrum? And one can get crude bounds on the spectrum and on the multiplicities of eigenvalues using a technique called contracted matrices, which I'll show you a little bit of. And then afterwards, one can get much tighter bounds and bounds on the corresponding eigenfunctions by adapting the existence proof that we just did for the fixed point itself. So there are two things I'd like to show. One is first this sort of crude bound, and the idea, if I can sketch it here, is firstly, we can use a sort of non-rigorous collection of approximate eigenvectors to come up with a coordinate change which puts our operator close to diagonal. Now I say close to diagonal because, of course, we're attempting to diagonalize something for all functions g in our ball, and therefore we don't have a single object to hand. We actually have a whole family of them. But the idea is to choose some nice linear transformation C that gets us at least close to something diagonal. And then the idea is, let's choose an integer little m, which is the number of specific eigenvalues that we'd like to isolate and bound. And the idea is that then we can come up with a sense of containment of a linear operator L in what I call a contracted matrix, which has the following property. If you pick a rectangle in the complex plane and your rectangle R contains one of the eigenvalues of your operator L, then evaluating the determinant on the right-hand side here using rectangle arithmetic will produce a rectangle guaranteed to contain 0. In fact, what we want to use to bound the spectrum is the converse of this. So if I can come up with a rectangle R for which this determinant is bounded away from 0, then I can establish that that rectangle does not contain an eigenvalue of our original operator. So I'll show you why this is a handy thing to do. We have our operator L that we would really like to bound the activity of, and we can consider a sort of one parameter family that connects L with a diagonal operator D. And the sort of family one can pick the obvious one of just multiply all of the off-diagonal elements by your parameter mu, and let mu go to 0. So that gives you something which is exactly diagonalized. And then the idea is that we want to show that as we move along this one parameter family from our operator L to this diagonal one D, none of the eigenvalues move outside circles that we put around them. So basically, perhaps I could sketch this. So we have our, let's see, we have our operator, we have eigenvalues that we're interested in outside the unit circle, and we have a number of other eigenvalues inside the unit circle. Maybe in principle they can be complex, although for this problem I don't think they are. And the idea is that we put a disk around each of these eigenvalues and a single disk around all of the others inside the unit circle. And then the idea is we want to show that as we move across this one parameter family from our approximately diagonalized operator to a fully diagonal one, none of the eigenvalues can pass outside of these disks by crossing the boundary circles. So to do that, we take the boundary of each of these disks and cover it with a number of overlapping rectangles, so produce a rigorous covering. And then we can use the criterion that I stated above. We simply need to bound the corresponding determinant strictly away from 0 on each of these rectangles for every parameter value in the unit interval. So one can do that by sort of dividing the unit interval up into subintervals. So there's this computation at the end that we can do, rules out the presence of any eigenvalues crossing these circles. So what we conclude from that is that L has exactly the same form of spectrum as D does, with the same multiplicities for the eigenvalues that have been isolated and the same bounded in the same locations, which means therefore so does the Frechet derivative dt of G. Okay, hopefully that was fairly clear. So this gives us at least crude bounds on the spectrum. But then what I'd like to do is to show that we can in fact do much better by just adapting the technique from the existence proof. So now that we've got disks that contain these eigenvalues, what I'd like to do is to bound eigenfunction eigenvalue pairs more tightly. And the idea is to embed the eigenvalue inside the eigenfunction. So our eigenfunctions are only defined up to some normalization anyway. So let's choose a normalization that embeds the corresponding eigenvalue as one of the power series coefficients, for example. So we pick some, I mean, well, there are many ways one could do this. One doesn't have to embed as a single power series coefficient, but this is one way to do it. So I'm going to pick some suitable linear coordinate functional phi and then normalize the eigenfunction in such a way that the eigenvalue is phi of the eigenfunction. So now we've got what's more obviously a nonlinear problem to solve in terms of the eigenfunction. Of course, the eigenproblem's nonlinear anyway, okay, in the pair v lambda, but now we've made it more obviously so by the presence of v in both of these locations. So then what I did is just to adapt the quasi-Newton method idea from the existence proof. So we'll write down a quasi-Newton method for this particular problem, for finding zeros of this problem, and prove that it's a contraction map on a suitably chosen ball around an approximate eigenfunction. So the details are here. I think perhaps they're not so illuminating. One forms an operator whose zero we're looking for. Here's its Frechet derivative. We'd rather not deal with second Frechet derivatives, so let's approximate it by some fixed linear operator, and that gives us a corresponding quasi-Newton method where we've fixed this operator in front here. And again, so we get a bound on the distance that our approximate eigenfunction moves under this quasi-Newton method. We get a uniform bound on contractivity, and we confirm the crucial inequality that tells us that this ball actually gets mapped into itself. So we essentially apply just the same method. So here's an example for degree d equals 4. And on the right-hand side, you see the corresponding eigenfunction. And the dotted lines I've just indicated using that, how the eigenvalue gets encoded by the normalization that we picked. So a natural consequence of this is that one gets rigorous bounds on the eigenvalue by evaluating this linear coordinate functional. And so we can get bounds on this delta within some particular interval. Okay, so that was all very nice, but I read a paper of Crutchfield and another by Schriemann and others, where they looked at the effect of adding on noise to the iteration of a one-parameter family, and there's an associated eigenproblem there too. So an obvious extension was to try to use this method to get rigorous bounds on the corresponding eigenfunction and eigenvalue. So what one does is one takes our one-parameter family, f mu, and modify the iteration of it to include a small amount of IID random noise. So one adds on these variables xi n, and we're interested in, or at least they're interested in, the limit epsilon to 0, so small noise. And basically one looks at the effect of the renormalization operator on this system. We look at what happened when we tend towards the fixed point function g star and take the limit epsilon to 0, and what you get out of it is another eigenproblem in terms of some particular linear operator curly L here, which in fact is very closely related to the Frechet derivative. So an intuitive way to think of this is that one takes the Frechet derivative and ignores the terms that correspond to variations in the constant a in your operator. And for the remaining terms, one squares the prefactors that appear in front of the linear perturbation. And the reason that this is the case is that one can write down an expression for the variance that results by applying renormalization to this system with noise in, and the fact that the added noise, these random variables, independent at each step, means essentially you don't get any covariance terms, you only get pure variance terms, and that explains why this square appears. So it's actually possible to derive this operator from the expression for the Frechet derivative in quite a systematic way. And then we take the same approach. So we embed the eigenfunction here, by the way, it's eigenfunction W has a role in explaining how renormalization redistributes the noise in the x variable, in the state variable, and the corresponding eigenvalue explains by how much one would need to tune the amount of noise present to keep things invariant, keep the total variance of the noise invariant as one moves to successive bifurcations up the tree. So this is an extra parameter we have to tune by a corresponding constant. So alpha tunes the position, if you like, in the x direction, delta tunes the parameter, and this new universal constant controls the amount of noise that we would need to put in the system. So using exactly the same method, we can find a bound, a fixed point to an appropriate quasi-Newton operator, and gain rigorous bounds on this new universal constant gamma, which controls the scaling of the noise. So I'll perhaps suppress the details because it's entirely analogous to what we did for the delta eigenfunction, but I can come back if anyone's interested. So we were able to apply essentially the method of Lamford with a few variations to bound the fixed point function itself for degree d equals 4 here, the eigenfunctions corresponding in fact to delta and alpha to the d, and also the eigenfunction and eigenvalue controlling how the scaling of additive noise goes. But then I thought it'd be interesting to try to improve these bounds and see how far that we could take them. So I made two independent implementations of this, what one might call the function ball algebra. One was intended to be a prototype, but as so often happens with prototypes, it turned out to be capable of doing the whole computation anyway. That was written in Python, and there, in fact, I used the decimal module because it provides multi-precision floating point decimal arithmetic with the correct directed rounding modes that conform to the relevant IEEE standard. And I made a second implementation in Julia that uses binary multi-precision floating point, again with the correct rigorous directed rounding modes to implement the interval arithmetic. It's useful in both of those languages to make heavy use of closures, particularly when implementing things like the Frechet derivative. So there are various sub-expressions that appear repeatedly in the computation for the Frechet derivative. So one wants to pre-compute those in an outer function and then have a closure basically over those for an inner function. So that was very useful to be able to use. And Julia also supporting multiple dispatch means the code is an awful lot cleaner, in fact, in that language. And around 1,200 different unit tests and functional tests sort of verified that the frameworks are doing the correct things. In terms of parallel computation, there is a technicality, which is that typically these directed rounding modes that one has to be very careful about are only safe at the process level, per process level. So if I can give you an example, if I'm adding two intervals together and I'd want to add their lower bounds, I need to switch into a rounding down mode, then add the lower bounds, then probably release that rounding mode back to round nearest or whatever the default is. Those three operations together are not atomic. If you're running, if you're using threads on the same process. So one could face a situation where the rounding mode is hijacked by a part of a computation in a different thread or something like that. So for that reason, where I used parallel computation, in particular for getting the derivative bounds, I only use multiprocessing. So then that protects the rounding modes within each process. Okay, so one can take this quite far. So for d equals 4, I was able to go as high as truncation degree 640, which gets you a function ball of radius 10 to the minus 331 around the fixed point, one of 10 to the minus 325 around the delta eigenfunction, and 323 around the noise eigenfunction. So every single power series coefficient, because these are L1 bounds, has at least that accuracy. And as a consequence, the various universal constants are bounded to within that accuracy. So one can come up with what I think are probably the first rigorous bounds on these universal constants beyond the first few digits. Here is the delta for degree d equals 4, 325 digits, proven guaranteed correct by this sort of method. So I thought it would be interesting to see with modern sort of techniques how far one can push these things. As I said before, for an actual proof to go through truncation degree 40 is sufficient. It's quite low, but it's interesting to see how high one can take these things. Okay, so given the bounds on one of these fixed point functions, there are many different things one can do. In fact, I've computed bounds on the spectrum for the original renormalisation operator, which involves some technicalities because there is no single disk domain will do, and one has to move to a union of disks and hybrid functions, but it's possible to do this. We were able to carry these computations through for other even integer degrees, in particular 2 and 6. Obviously, as one goes to higher degrees, the numerics becomes more difficult. Finding an initial domain and dealing with the power d in the numerics is complex. And one can adapt this to odd integer degree critical points basically by tweaking the functional equation. And we've used this to, a paper of Feigenbaum showed that the attractors at the accumulation of the period doubling cascade can be expressed as the limit set of an iterated function system defined by a pair of maps. And those maps depend on the inverse of the fixed point function g. So we were able to implement these iterated function systems and get rigorous bounds on the Hausdorff dimensions of the corresponding attractors. But the real sort of motivation for getting into all of this in the beginning was to look at coupled systems. So if time permits, I could describe some recent results on coupled systems. In particular, the simplest case is to think of the unidirectionally coupled systems. So here's what the renormalization operator looks like acting on pairs of maps in 2 variables. So now one has a pair of functions g and f that one is composing with itself. So one gets g applied to g and f applied to g and f, first and second components. And then one independently scales the first and second components by constants alpha and beta. So this is the so-called doubling operator, if you like, on pairs of maps of two variables. And as before, one can define these scalings to preserve some sort of normalization that we're interested in. And I've picked the obvious one that will let the function values be 1 at the origin of these two maps. Now, there are many different fixed points for this operator that one could study that we're interested in, all corresponding to different universality classes, different types of dynamics. But one of the simplest is to pick the following ansatz. So this is relevant to the so-called FS type universality described by Kuznetsov and others. So one picks a particularly simple form of unidirectional coupling here. And essentially, we've reduced the first component to our original renormalization operator on single maps of a single variable. So now we have this, if you like, skew product structure where the first component just corresponds to the usual Feigenbaum renormalization operator. And we have a particularly simple form for this second function f, where the way that it varies with the second variable y is fairly trivial. The renormalization operator preserves that structure. So one now has a corresponding operator induced on these functions f tilde. So now we're interested in finding non-trivial solutions of this functional equation. So we can solve the first component for a fixed point by using the solutions we got for the operator we already studied. And in fact, we have those bound very tightly within particular balls of functions. And now what we'd like to do is to solve this problem for this unknown function f tilde. So Kuznetsov and others have studied this extensively numerically. And in the degree d equals 2 case, the non-trivial solutions that you can find include, well, the first is just dependent on the usual Feigenbaum fixed point function in a very simple way. So this is just the solution we already had, minus x, essentially. And the scaling constants are equal, alpha and beta are the same. But Kuznetsov and others also conjectured that there's a second even solution with corresponding to another universal constant that controls this so-called FS type scaling behavior that one can observe in families and maps. So it's this one that we would like to prove the existence of. So we want to find a non-trivial fixed point of this operator curly k here. Since we're interested in even solutions, we can just make this ansatz and work with the corresponding operator acting on functions capital F tilde. So we come up with this operator k acting on these sort of symmetry reduced functions. And capital G star here, of course, is the function that we've already bounded tightly within a function ball from our earlier computations. So that it's this thing that we would like to find a fixed point of. And using exactly the same method again, using a suitable quasi-Newton method with truncation degree as low as 20, we've been able to prove the existence of this solution. And one gains, taking a ball around the Feigenbaum fixed point function of radius around 10 to the minus 11 gives you a bound on this second component around 10 to the minus 7. And in the diagrams, I've shown you how the corresponding function little f looks. Incidentally, we only have a fairly small initial domain omega here. For the case degree d equals 2, omega is a disk centered on 1 of radius 2.5, but you'll notice that I've been able to sketch these functions over quite a large range. So what one does to do this, of course, is to write down recurrence relations using the fixed point equations for our operators. So for example, one knows that G star is R of G star. And so one can write down a sort of recurrence relation, which together with our domain extension conditions implies you can take analytic extensions to larger and larger domains. So this is how we produce these pictures over large domains. And then pushing things, at least as far as I have so far, it can go up to degree n equals 160, which gives us a bound in a function ball of radius around 10 to the minus 93. So we gain around sort of 93 digits worth of the corresponding universal constant beta we can find exactly. Okay, and our current work or our more recent results are to do with the so-called bicritical fixed point, which is another fixed point relevant to a different universality class of behavior for this operator R on pairs of functions of two variables. Okay, so I think I'll conclude there for now and ask if there are any questions. I'll just put a reminder of acknowledgements to my team. Andrew Oswald-Eston and Judy Thirlby in particular. I've put some references to recent papers which are on the archive. Thanks very much.
Thank you, Andrew. Very nice talk. Okay, well, there's plenty of time for questions. People have questions.
So Andrew, thank you for very nice, clear talk. One thing that, you know, has always fascinated us and we could never establish or prove is that when you look at the spectrum of period doubling operator, I think we computed between 30 and 100 eigenvalues. I don't remember the total number. It's all real, which is very weird because this is not a self-adjoint operator, and it would be wonderful if it could have been mapped into something, or it could be just a triviality because the half of the spectrum is trivial. It's the alpha to the power, you know, scaling eigenvalue, coordinate transformation eigenvalues, and all the other eigenvalues are intercalated between them. So maybe they cannot float off into the complex plane. So do you have some thoughts or results in this direction?
I think this would be really interesting to prove. Yeah, I'm aware of this problem. I'm not sure if these methods could be adapted. I mean, the contracted matrix technique, one could try to bound the eigenvalues within ever tighter strips containing the real line, but to actually prove that they're real, one wouldn't be able to do that with that approach. But yeah, it would be very interesting to try to understand why they all seem to be real. I don't have a good intuition for it, though, I'm afraid. It'd be nice to see some reason which made it in retrospect obvious, I think.
Thanks.
I have another question concerning the start. So you made, when you were hunting for this fixed point G star, you immediately jumped into the business with analytic functions after realizing that polynomials don't work because they only give trivial solutions. But do you know that the G star is an analytic function a priori, or is that could there also be other fixed points which are non-smooth?
Yeah, so I think there are other fixed points in other classes of function. So what one can look in, there are papers which look at this same operator in completely different function spaces. One can even look at things which are only piecewise constant functions, things like that, and come up with some very interesting alternatives. Yes. The moving to analytic functions sort of feels like an obvious thing to do when one looks at it from the viewpoint that polynomials can't be anything other than trivial solutions, but that's not the only direction that one could go in, that's for sure.
So does it mean that there could be many fixed points and you are hunting for one of them by an analytic ansatz, and the others, well, you don't know about, right?
Yes, in principle, yes. And I believe that there are completely different characters of fixed points to this. The question would be whether they then are relevant for particular sorts of universality that you observe. So I guess that would be the second question. Yeah.
That's the second part of my question. How do you know that your fixed point is responsible for the universal constants and not others?
That's a good question. Yes, I mean, I mean, one could view analytic functions in some sense as physically relevant ones. I think that's one way to look at this. But yeah, there is nothing to rule out that in a much broader class of systems that one doesn't have corresponding universal things happening. Yeah.
In this context, Henri Epstein has beautiful work using Herglot's domains.
Yeah.
And, you know, so analyticity is very nicely under control for the class of functions that one is interested in. The reason why they're smooth is because, you know, this is measured in experiments in physics as a, you know, unimodal kind of functions going through period doubling sequences. So you have no reason that I'm aware of to hunt for other non-differentiable kinds of fixed points. But and I think Epstein works, you know, uses analyticity in a very powerful way.
Yeah, but
So I'm never worried about it.
Physical experiments cannot be taken to justify analyticity. You see, so that's then you want a real proof, right? And so if
no, of course, but you know, I'm just saying the problem actually comes from you know, observing helium boiling and stuff like that. You know, it has a physical basis. So that's why one chose analytic functions at the start. But I think as a purely mathematical problem, it still has, you know, there's very strong reasons to assume analyticity.
Sure.
I mean, one thing that the approach I presented doesn't contain is the bifurcation parameter. And I think Epstein's technique also, one can write down a sort of fancier version of the renormalisation operator that acts on pairs, not only the function, but also something representing the bifurcation parameter. And one can then prove that one has a contraction map on this sort of augmented object as well. So that's a different way of approaching this. So in that setting, the delta would not emerge as this unstable eigenvalue. It would be encoded as part of the action of your operator on these pairs. So that's a different way of formulating the problem again.
If I may ask another question, this is concerning when you are enclosing eigenfunctions and eigenvalues, you're using this normalization, lambda equals phi of v. So, and this is, at least in my experience, a bit unusual normalization. So usually people take any normalization and then take so add a normalizing equation to the system and then take the pair lambda comma v as unknown. And is there any specific advantage of this special normalization, or is that just for fun, or why do you use that instead of studying the augmented problem as people usually do?
It appealed to me on sort of symmetry grounds in a way that it's somewhat analogous with the universal constant alpha and its partner a, which is 1 over alpha. You know, a is g at 1. So in a sense, the original Feigenbaum function with our normalization produces something akin to an eigenvalue when you evaluate it at the point 1. So actually, for the degree d equals 2 case, it's interesting, the center of the disk domain that it's nice to choose is also 1. So one gains analogously, one gains delta as the value of the eigenfunction v at 1. So in some ways that appealed to me, and it also was convenient because then one doesn't have to think about this space of pairs of eigenfunction, eigenvalue. One can simply realize that we've got this extra degree of freedom anyway. So let's embed the eigenvalue. One could pick different coordinate functions, different functionals. In fact, they need not be coordinate functionals, and I did wonder whether numerically there's some advantage to be had in that. in a sense, the eigenvalues that I find are a single power series coefficient of the eigenfunction. And would one get different sort of numerical behavior if they were, for example, the sum of power series coefficients or something like that, if one picked a different normalization? I'm not sure. But yeah, there was some appeal to me that A is G at 1 and delta is V at 1 and gamma is W at 1. That sort of, that there are these pairs of objects related in an analogous way.
The only thing you have to take care about is that the phi acting on the true eigenfunction is not 0.
Indeed, yes. Yeah, so first, of course, one numerically computes good approximations to these things and convinces oneself that indeed you've picked a non-zero coefficient. Yes, yeah. But I guess that what I'm getting at, there's a sort of symmetry in my mind between the degree of freedom one has in normalizing an eigenfunction and the degree of freedom one has in normalizing G star itself. That there's, in some sense, this is analogous.
Any other questions?
Well, actually, I have one more, but
Fire away, Michael.
so you computed this operator C, which makes the dt of G approximately diagonal. That's how you said it, right? And that is has to be taken over a set of G's, so to say. And how do you compute that C? Is that you just make some attempts and then estimate a good operator C, or how do you do it?
Yeah, I mean, one can actually take just a non-rigorous numerical approximate eigenvectors and construct something, a block diagonal operator whose sort of upper left block, the polynomial part, is made out of these approximate eigenvectors. And
what you plus, but you have that over a whole set of operators.
Oh, so yes, absolutely. Yeah. So then one has to evaluate the Frechet derivative at each of these new basis elements, if you like, to calculate the action of the Frechet derivative on C. Yes, and what one gets out is sometimes not very close to diagonal as a result of the fact that one is not applying this to a single function, but to a whole family of functions. And in fact, in the Siegel disk renormalization problem, which is what I studied for my PhD, we were not able to bound the spectrum using this technique because the operator that we gained was too far from diagonal with respect to the basis that we'd managed to pick. So this is, as you say, there's a bit of a rule of thumb involved here. It's a procedure that if it works, it's guaranteed correct. If it doesn't work, you don't know if it's because the bounds are too loose or you picked a bad choice of operator and so on.
Can you not work by subdividing in some sense the set of the set of functions where you have to take the operator on, subdivide in regions, and then do this compute an operator C for each of these subdivided regions? Then you could come closer to diagonal, at least piecewise.
Oh, that's an interesting idea. I mean, the set of functions, of course, is infinite dimensional. It's a ball.
Yeah, of course.
So, but perhaps it might be possible to do that in some way.
You cannot subdivide into small pieces. That's clear. Yeah, because it's but nevertheless, maybe in strips or so. Okay. Anyway, thanks.
And these all these Julia libraries are available online?
The ones that we created? Or... Yeah, I haven't released them publicly yet, but they're in a GitHub repository that goes along with the preprints. So when the preprints become bona fide papers, bona fide research papers, I'll make them public. Yeah, but in the meantime, if anyone is interested, I'm happy to share in advance the libraries. So For the Julia one, I mean, I wrote my own interval arithmetic on top of big float, because big float provides the correct directed rounding modes. But I'm aware that I think David Sanders has an interval arithmetic package. I would be quite interested in using that and comparing whether it gives a performance increase, because big float in particular is really wasteful in terms of allocations. And so a huge amount of the time, processing time, seems to be spent allocating and deallocating objects. So it would be nice to have a pure Julia alternative, in fact, that would where these things would get optimized away. For Python, I used the decimal module, which might seem a bit strange. Originally, it was a toy implementation, which would have the advantage that the bounds it produces, you can simply quote them, rather than having to convert from dyadic rational binary approximations to a nearby decimal. But it turned out that it's actually quite good. You know, it was certainly enough to do all these proofs up to a fairly high truncation degree in Python using the decimal module. But again, it implements the correct rounding modes, which is very useful. And yeah.
You didn't say much about how long things take, like these super high precision calculations of the constants, you know, where you have 10 to the minus 300 accuracy and things like this. Yeah. Can you just give us some sense of how long those things run? Yeah,
that's of the order of a week on my desktop machine, which has 8 cores. It's a sort of i7 8 cores machine. RAM can become significant if one is trying to, so one wants to parallelize the evaluating the Frechet derivative of the Newton operator is the big computation. And so one has, you know, for degree 640, you have 641 basis elements on which this expression needs to be evaluated separately. And it's CPU intensive, of course, but also one's limited by the number of processors, and because it's CPU intensive, it only makes sense to run one process on each processor.
And that calculation was done in both Julia and Python?
Yes, I took, well, Julia was around a week, I think, and the Python was longer for that one. Yeah, it's considerably slower, but
so maybe, yeah, maybe other libraries would be interesting.
Yeah.
Any other questions? Well, Andrew, for myself and the organizers and the you know, the audience, thank you once again for a really nice talk today. Yeah. And it's nice to see everybody sticking around. You know, it's nice to chat after these things. So this will be now sort of the first break we've had in a year of running this thing. I think we took a short break around the holidays, but not very long. So now we'll take probably a month and a half, maybe 2 months off, and we'll send out some emails in the fall and kind of see if people, how interested. You know, we'll have one in August or September and see how interested people are in keeping this going. So, but otherwise, it's been a great year, everybody. Well, not a great year, but a great year of this seminar. This seminar has been a highlight of the past year for many of us. And we'll see everybody again, hopefully soon. In the meantime, I hope everybody gets a little break, has a little vacation. Cheers.
Bye. Thank you very much, Jay. Thank you very much.
Yeah, it's a pleasure.
Have a nice summer, everybody.
Yeah, you too.
Have a nice summer.
Okay, well, I'm going to jump off, Andrew, but it was really nice to meet you, and I hope to see you in person and chat about these things more, you know, before too long.
Yeah, that would be great. Thank you for inviting me as well. I think I kind of rushed through it a bit, but
no.
I didn't know how familiar people would already be with all this Lamford type proofs. So
it's really good. And like to to me, like having some of these nice renormalization talks recorded for students to view in the future is incredibly valuable. So it's really nice.
Yeah.
Thanks.
See you, Michael. Always good to see you. Oh, we don't hear you.
Same vice versa. Thank you.
Yeah, okay. All right, everybody. Cheers.
Bye-bye.
All right.